Welcome to Coding Adventures. Today we're gonna attempt to create this interesting effect, graphical effect, in about 100 lines of JavaScript. Okay, so let's start it. Alright, I'm back and I'm gonna open my coding editor. And here we're gonna write the code using shapes and animations in order to achieve that effect. I'm calling that one mutual connections because of the various balls or particles that are moving on the canvas and they try to connect to each other once they get into close proximity. Alright, so perhaps actually before writing the code, let's plan a little bit on a piece of paper what we want to achieve. So this is our canvas. I'm representing this as a rectangle. And the canvas that we are using here has basically a resolution of 800 by 600 pixels. And we plan to create at random positions various particles. Or I'm calling this one sometimes balls or small circles in essence, right? And these circles or these particles are going randomly on the screen. So they go in random directions. Actually, they can go, on diagonal. It's mostly on diagonal they go, and they just go. And once they hit an edge of the screen, they reflect back, and they move this way, and they hit another edge of the screen, and then they move this way, right? So we implemented this kind of effect many times in the past, but the novelty here is that once a particle gets close to another one, let's say this one. Once it reaches this point, once it gets to a certain distance from another particle, it will create a connection or a line to that particle. And if here we encounter another particle, basically we create a connection to that one. And not only this one to this one, but actually any particle to the other one. So this will be represented basically like this one. And once the particles move further apart, these connections will basically not be displayed. Alright, so that's our kind of basic design for this effect. It's pretty simple to implement it. We're gonna create first of all here in the code a number of particles. So let's define a few constant basically, shall we? So const number of particles. Perhaps we should start with, let's say, 35 particles, just an arbitrary number here. And these particles are moving randomly at a certain speed. Let's say the maximum speed is basically 3 pixels. And we can also define some constant for that distance when the particle gets closer to a certain distance. Okay, let's define that one as well. So basically distance from distance particle, these particles. 100 pixels. We can tune these variables however we want to achieve a much nicer effect, but for now we're gonna start with this one. Alright, so other than these constants that we're gonna use in our program, let's define here an array of particles basically, or should call it just particles. That is an empty array, and this array we're gonna plan to populate it with basically up to 35 small objects that will keep the information about each particle, right? So let's have a function, perhaps function create particles. And this one is supposedly we're gonna create the particles. So we'll have how many particles? First of all, we can pass this one as an argument here, n particles, right? We want to create n particles. So we have a counter that goes from 0, I less than n, I plus plus. And now we're gonna create a particle, like an object, like an inline object. And this object will keep a few properties. First of all, each particle will have a position on the canvas, an x and y. So, and this will gonna initiate them with random values initially. So this one, it's a random, can be random of 800 on horizontal, or we can use the constant width, which basically gives us the width of the canvas, which is 800 anyway. But just to make the program more generic and avoid hard coding constants, we can use this or avoiding numbers, we can use this constant. And y, it's a random using height here as property. Now, the way these particles are moving, and maybe we should recap again this kind of logic for in which we are moving the particles. So if we are getting back here to the drawing board, and we'll draw just one particle, so this one at any point in time will have these x and y coordinates, right? So these are the coordinates of the particle. And for each frame, because we planned basically to run this in an animation loop, what we're gonna do, we're gonna add to these particles two constants, dx and dy, which is basically, let's say these are the delta x and delta y, or can be considered the speed on x and speed of y. So let's say dx is 1, and if dy is 1, what will happen? So dx is 1. I'm gonna draw some gigantic pixels here. The next pixel will be here, and dy is 1, the next pixel will be down 1. So basically here will be the next position, right? So basically the ball will move with 1 pixel on horizontal and 1 pixel on vertical each time. So basically the ball will go in this direction. And once it hits the bottom of the screen here, what we plan to do is to inverse the dy, basically the delta that goes on vertical. So this one will inverse it and become -1. Dx will remain 1. So dx remaining 1, basically the particle still advances to the right, but dy becomes -1, so the particle will move in this direction. It's like it's bouncing off from the edge of the screen. A pretty simple logic, and we can code it very easily in the code. So for each particle, we can keep this one dx value, and we say dx can be either 1 or it can be -1, and we'll just choose to select two random numbers basically, or a random number between either -1 or 1. We'll use random with an array specifying -1 and 1. So automatically we're gonna pick any number from this array. We don't know where the particle will be heading. And then we'll have the same kind of logic for this one. So for the vertical one. So we have dx and dy. What can we have here? First of all, because we selected dx as being -1 or 1, it's okay. Sometimes we prefer to do it this way because dx has also a meaning of direction, and -1 and 1 are enough to kind of represent the direction. But if we'll try to just add x with dx like we did on the paper, the particles will move very, very, very slowly. So either we basically modify here. So for instance, we select, okay, these are the two values for the dx, which is okay. Or we can have another kind of property of the particle, speed. And actually, yeah, I was prepared to say speed is 3. So the particles will move all of them at the speed of 3. But since we defined anyway a constant here, max speed, we can use this one. Or even better, we can make the speed a random number between 1 and the max speed, right? So I think that's enough all we have to keep about the particles. We don't have to keep colors or any other attributes or properties at this time. We can add them at a later time if we intend, but for now, this is enough. Let's just put them really quickly, push them into basically an empty array and return that empty array. So we can do either that, so we can have an empty array here, and basically we're gonna push this particle object in the empty array and then return the empty array, and then outside of the function we can assign the empty array to this, or that return of the create particles to this one. It's good. Yeah, perhaps you should do that. Or we can just access from inside the create particles the global variables, which is also okay in this case. It's a small program. So yeah, let's do that one. Let's access it from within the create particles function. So all we have to do here, say particles, push. Actually not at the end here. After we create each particle, we're gonna push it into the array. All right, so right now we should have the particles after we call the function. As a matter of fact, we'll call it here with number of particles as argument. So we should have it, but if we run it, we should not see anything on the screen, which is normal because we are not rendering anything. We are just creating an array in the memory. Let's name this one mutual connections. I like this name for this kind of effect. So how can we know that we basically created the correct number of objects? Well, a very simple way is here we can put a println here. Let's check now the length of this one, of this array. Should contain the, yeah, 35. Probably they are the right objects inside. But in order to make sure they are the right objects, what we can do right now is basically create another function that will gonna just display them. So let's create it, yeah, perhaps after this one. Function display particles. And this one is a pretty straightforward function. We're gonna just loop for let particle p of particles. We access also again the global particles array, and p is in this moment an object because the particles array contains objects. So we iterate to it and we just draw a circle at a certain coordinate. We can draw a circle at p.x or p.y, something like that. Yeah, maybe you should draw it. Circle p.x, p.y, and a certain radius. Yeah, let's have it as a constant here. Particle radius, let's choose 10. Big particles. Usually when you see this effect on internet or on websites, usually they use very tiny small particles. Well, perhaps we should create a different variation of it with bigger particles, chunky ones. So let's put it here. And just to be sure, we can have a certain stroke, a certain fill. We can fill it with white, just to make sure that, you know, we display it correctly. And then the line is black, the circle stroke is black. So that should be okay. We should call the function display particles. Let's just call it here, right? Just to see the initial state. All right. So we have the particles display on the screen. They are non-moving, but this is basically the initial state of the array with the particles that we draw there. All right. You know what I don't like? I don't like that this black is too black. We can display it in a shade of gray. And either we write here gray, like a name constant, but also if we want to create shades of colors, we can choose number from 0 to 255, right? 0 meaning black and 255 meaning white. As a matter of fact, instead of white here, we can just write white. And if we want black, we put 0, or we'll, yep, is the same, or we'll put here a number in between, like a lighter gray. Yep, let's say our particles have this color. And again, like we said, we can tune this color later on. All right, everything is in good order right now. We created the particles, we can display them, let's animate them. Basically, we're gonna create a function update particle that we're gonna run it in a loop, and we're gonna implement that logic for each frame. We're gonna add to the particle x, the particle dx, eventually multiply by the speed, just to make sure that they move at the right speed. And then we're gonna check for collision with the edges. All right, so let's set up another function, update particles. And inside, what we are doing, we are also looping through all the particles. And then we add, like we said, to the x position of the particle, the p.dx, eventually multiply by, by the particle speed. See, each particle have a different speed because we put a random. We don't have to multiply by the global, or we cannot multiply by the global one. We have to use the speed of each particle. So it's p.speed, just like that. And then we do the same with the p.y, multiply by p.speed. And if we have to check with the collision of with the edges, otherwise we're gonna lose all the particles. But let's just run it just for fun. All right, oops. This function is not called. In order to be called, we need to implement the loop function. And loop function is a special function. We don't have to call it ourselves. The browser will call it for us up to 60 times per second. So all we have to do inside this function here, we have to clear the canvas, call eventually display particles, and then update particles. or the other way around. Usually it's better the other way around, but works also this way. So let's run it. All right, particles are moving. They go outside of the canvas, and soon the last particle will go outside. All right, it is okay. What we can do at this point, actually, we can either bounce them, or if they leave the side of the screen on one side, can appear on the other side. That's another possibility, but the idea is to keep them within the visible canvas in a certain way. So let's try to bounce them for now, but if we want, we can implement also the other effect. So if p.x is greater than width, right? So it's trying to go on the right side out, or p.x is less than 0, trying to go out to the left side, we just say p.dx, we multiply it by -1. This is for bouncing. And if we want, we can do the same, or actually we have to, for p.y, and then the dy becomes -1. So the particle should now bounce on the edges of the screen, and we are not losing any particle. Like I said, if we want, we can change the logic here. So we can basically, instead of, we don't even need the direction at this point, or actually we need the direction, but we don't inverse the direction here, but we actually change here p.x become a new value. But we'll have to check each condition independently. The width, if it goes to the right side, make it appear on the left side. If it goes on the left side, make it appear on the right side. So a little bit more code. So it's fine. With bouncing is fine for now. So at this moment, we have these happily bouncing particles on the screen. All we have to do is kind of create a rule. When the particles are moving, each particle should check if it has connections with another particle. So what it means to have connections with the other particle, if we move back here, it's basically if we need to see if a particle is within the range of other particles, is basically this effect here, right? We need to make sure that, or we need to check if a particle, for each particle actually, not only for this one, we just choose this one. So for this one, we have to check if it's close to any other particle. Then we go for the other particle and check if it's close to any other particle, right? So in essence, for each particle, we have to check if it's close to other particle. This kind of logic is a little bit, some of you may already see that it's a little bit heavy. So basically we do a lot of comparisons. So if we have here 35 particles, for each particle we check with the other 35 or 34, because we don't check with itself, right? So there are lots of comparisons done for each frame, right, in order to create those connections. There are more performant algorithms, but this one is pretty simple, and we should implement it just like that. All right, so what we have to do, we said for each particle, so perhaps it's a good opportunity here to go inside the display particles. And after we draw the circle, we draw the actual particle. Let's say we want to invoke a function to display the connections of this particle to other particles. So we're gonna call a display connections. And this one should take as an argument a certain particle, in this case the P. We are still inside the for here, right? So we want to display the connection from this particle to the other particle. So we're going to implement this function, and inside this function we're going to do another loop to loop through the other particles, which is, again, like I mentioned, lots of calculations for a single kind of frame. So let's have it, it's called display connections function, display connections, display connection from basically this particle P. We can say it from P, right? So display connections from particle P, because right now we're going to loop to all the particles again. So and now we want to check, of course, if this particle is equal to one of these particles, we don't do anything because we don't draw a connection from itself to itself, right? So that's one thing that we'll do. So if P equal from P, and now it's an interesting keyword that we're gonna introduce here, is called continue. Continue is similar to break in a sense, but break just breaks out of the for, the execution jumps after the for. Continue, it's pair keyword, to say like that. Continue will make p advance to the next value, right? So we skip over p in a sense here. And we could have write the logic differently. We could have say if p is different than p, and then we're gonna put a big code block here to do all the logic. But I just prefer like this one, just to clarify really quickly if p is different than from p, and then we move our way, right? So at this point, all we have to do is to calculate the distances from each p to the from p. Now, let's remember, each of these objects, they have inside the p.x and the p.y. So, and the other one has from p and from p.x, from p.y. So we have basically 2 points on the canvas. We can calculate the distance using Pythagoras, very simple. We did that in a past episode. But we can also make use of the function dist that is available in the p5.js library and then in CodeGuppy. So that will give us the distance. So let's say the distance, d, is the distance between 2 points on the canvas. So the first point is p.x and p.y. And the other point is from p.x from p.y, right? So these are the 2 points on the canvas, and let's find the distance, right? And what we are doing with the distance, we should check against this. When we started the program, we said, okay, we're gonna check if the distance is within a certain range, and we define a constant. What is this one? Distant particles. All right, so let's compare it here. We come back and we say, if the distance is less than distant particles, less or equal, it's irrelevant at this point. 1 pixel won't make a big difference. So what we want to do, basically draw a line. First of all, draw a line. So let's draw quickly a line from p.x, p.y to from p.x, from p.y. Let's draw this line. Let's see the effect, and we'll run it. Let's save it. Mutual connections, and let's run. It's pretty cool, right? See, that's why I like to call it mutual connections, because this particle effects creates this, once the particles are moving, it's like a network of people. Once you connect to other people, and when they get closer to you, you create these connections. Now, we can consider the effect finished, or if we want, we can just enhance it a little bit, perhaps with some colors or some other, some other kind of interesting effects, right? So let's see, what can we do here to the code? Perhaps we can draw we can fill the 2 circles, right? The circles that get connected, we can fill them with a certain color. So let's run it again and look at the effect. Yes, once they get closer, let's also fill the circles. Let's make them, instead of being transparent, let's fill them. So what color should we choose for filling? Let's just fill them with a constant right now. We just choose fill 150. For this one, we're gonna do stroke 150. We'll do the line. The line is fine. Actually, let's do the circles first. Let's fill the circles first. Yeah, or we do the line, and then we can fill the 2 circles. So the 2 circles are these ones, px, py, and radius. I think we have it like a constant, particle radius. Yep, particle radius. And then we can fill the second circle also with that value. But see, this fill will remain forever, so all will get filled. Actually, no, they kind of yeah, they don't remain filled, because initially when we are displaying, we are filling here, we are overwriting that one, so it's fine. Yeah, so I think this one looks a little bit nicer, although you know what we can do? We can fill them with a shade of gray that is kind of dependent on the distance, right? So if the distance is 0, it's black, right? So they get close, it's black. Once they get further apart and they get closer to one particle distance, maybe the shade should be 150, right? And in between should be a shade in between. So what we can do, we can have, we can use the map function here. Yeah, we can use the map function. So let's have the color, and we are mapping the distance that goes from 0 and up to this value. We'll map it to a value that it's in the range 1 to 150. So map its kind of color at this point. It will be a value in the range 0, 150, proportional with the actual distance, right? So instead of filling with 150, let's fill with this color. And we also do stroke of that color. I like it. Do you like it? So now at this point, you know, we can play variations on this program. We can increase the number of particles. What about 50 particles? You know, it's 50, or you know, we can make particle radius indeed really small, tiny. So, and maybe we can increase the number of particles. We can make the background a certain color. Some people, I like, yeah, let's try background red, but then probably we'll have to, it's too reddish. We have to work the colors of the lines. We leave it white here for now, because otherwise we have to tune the other colors. Personally, I like bigger particles in this case, but you know, feel free to play with this, play with the distances, and see what effect you accomplish. Eventually, you can place even one of these nice backgrounds if we want, background shapes, so the particles will float over that one. Background shapes. This is just an image, but you know, these particles actually can be displayed on top of things, can be displayed on top of images, and if you want, you can implement it and bring it in a website and display it on top of other HTML elements. And you know, it's up to you what you want to do with it. So let me share this program with you on the chat for now. I let it running for you to enjoy it. So let me name this one particles, actually mutual connections. Mutual connections, just like this. All right. So I hope that you liked the today exercise and have fun, play with it. But wait, I have an idea. Let me save a copy and let me try to create a variant of this one. So I'm thinking now, instead of the particles to connect between themselves, I'm trying to connect them to the mouse pointer. All right. So let's do another variation on this one before we closing the episode. So let's make the particles a little bit small, because we can leave them like that. 10 doesn't matter. So we want to connect, we said, to the mouse pointer instead. So obviously here we're gonna display the connections. We don't display the connections between the particles. This one goes. Actually, we need a function to display the connections. Let's call it after the for this time, because we are not having to check with all the other particles. All we have to check is we have to check the connections with the mouse, so with a single point. So basically, we're gonna check with mouse X and mouse Y, which are the connections, which are the coordinates of the mouse pointer. And let's see if we can basically repurpose this function, or we have to recreate it. Yeah, I think we can repurpose. So what we have to do right now is to draw these lines between from a certain point to a certain point. So it will not have a particle here, but let's say it's from an X, from Y. And now each time we're gonna calculate the distance from a point, and instead of a particle, from Y. And here we have to do the same. We have to do a few modifications, and if we are correct, we should obtain the effect that we are intending. Let's change it really quickly. From X and particle radius, let's run it. Oops, from P is not defined. Where is that from P? Oh, right. We don't need these verifications anymore. All right. So see, I'm moving the mouse on the canvas, and those connections are automatically formed, or I can even leave it in a one point. As particles are moving close to my mouse, the connections are formed. So let me make the particles a little bit smaller, perhaps this, and increase the numbers of particles, 50 or even more. Yeah, I like more. Let's create 100 particles here. It's like a walking spider. It's like a spider that is walking really carefully on a bunch of moving pads. As I'm moving the mouse, all this effect is achieved. And now we can make this one move slower or faster. We can, let's say, random of 1. They move really slow. Or we can make the speed 0.5. They should move really slow. Unless here we have the random, yeah, between 0. So maybe the random is between 0.1 and max speed. Now, yeah. So we can move nicely with the mouse over all these particles. Let me save this one. Mutual connection 2, or actually this one is mouse connections. Mouse connections. And I'll have it on the chat. Let me write here, mouse connections. All right, so which one do you like the most? This one or the other one? Let me open the other one. The other one is automatic, mutual connections. Let me place it on the side here, run it, and this one I'm playing it myself. All right, so that's all for today's lesson. I hope that you like this nice effect and you learn a little bit of JavaScript, and in the future you can take this one and place it in a website as a background, perhaps to a web page, or it's up to you what you are doing with this effect. All right, feel free to extend the programs, and if you are doing anything interesting, any other visualization, perhaps if you introduce colors, feel free to put a link in the comments. Hello to all of you, hello to Brazil, and with this one I'm just saying happy coding, thank you for watching, and see you next time.